Well, my students, today we shall review again special relativity. We have begun reviewing special relativity in the last class. Today also special relativity review. Today we shall discuss two important facts about special relativity, which are consequence of Lorentz transformation. Say, I have a rod and these two frames in standard configuration. The rod is in the S prime frame and the endpoints of the rod are XB prime, XA prime. This S prime frame is moving on the right side with velocity V. The L node is called the propel length. L naught is called the propel length. What is this? XP prime minus XJ prime. This is the propel length. Now we want to know what an observer in S will assign about the length of the rod. What will be the length of the rod viewed from S? So we take Lorentz transformation. And we take direct Lorentz transformations. We don't have any other way to take. We have to take direct Lorentz transformation. And here x prime a, that means this part. X prime a is gamma xa minus vta. Actually, in the last class we have used here beta, so it is not a problem. It is not a problem. Right? Give you as C divided by C beta ct, except in the form of the last class. So this is x prime a, this is x prime b, gamma xb minus vtb. Now condition is from S the observer will measure this point and this point at the same time. He cannot measure these 2 points, x prime, x prime, in different times. He has to take these readings at the same time. So condition is Ta equal to Tb equals T. So here Ta, Tb are same. Okay. Then xb minus xa is what? 1 by gamma, xb prime minus xa prime. These 2 terms cancels. So we get xb prime minus xa prime is what? L naught and 1 by gamma. L naught 1 by gamma. Also you can write it here. You can write it like L equal to L naught square root of 1 minus b square by c square. You can also write in this way. So this is your length contraction. Why? L naught is the proper length multiplied by factor fraction. Square root of 1 minus b square by c square is a fraction less than 1. So which is bigger? Bigger is L naught. L naught is bigger, L is smaller. So proper length is the bigger length. And the length seen from another frame is less than the proper length. So this is the length contraction. This is the law of special relativistic effect. Now come to time dilation. I have 2 frames. Actually here you see 3 figures, but actually we have 2 frames only. This is the S frame, this is the S prime frame. In the S prime frame, at location S prime A, there is a clock. The clock clicks first in this configuration. Click 1. After that T naught, it moves little further. But since the clock is in S prime and phased, X prime is same. The clock remains stationary at the position S prime A and clicks the second time. The difference in time between click 2 and click 1 is T naught. So these two actually TB prime. Ta prime plus T naught is Tb prime. But we have written here Ta prime plus T naught because Ta prime is the term click 1, click 2 is Ta plus T naught because we have said that the difference between the two click is T naught. So we have to take care the inverse Lorentz transformation. There is no other way because we have to implement condition x prime equal to x prime because in the s prime frame the clock is at rest at x prime. So x prime cannot be two things. The clock is in the s frame fixed x prime. Although we have written here x prime for following Lorentz transformation, but in actual reality x prime is the same thing that the clock is. Okay, now Tb minus Ta, this term cancels out because x prime are same. This term cancels out, this term cancels out, gamma multiplied by T naught. Or gamma is 1 by square root of 1 minus c square, T naught by 1 by T naught by square root of 1 minus square by c square. This is time dilation. Why? This T naught is called a proper time. Why proper time? Because it is the time recorded by a single clock. And this Tb minus Ta, this time is by two clocks. When this frame's clock coincides with this point, it gives Ta. When this frame's clock is coincident with this, it gives Tb. That is, in S there are two clocks reading. In S the reading is from two clocks, for Ta, for T. But in S prime the reading is by one single clock. Okay? Now what is T naught? T naught is a time recorded by a single clock, so we call it the proper time. This is the proper time. That means a clock in the S prime frame, moving clock. This is the time given by the moving clock. The S prime is moving, so the clock is moving. T naught is the time given by the moving clock. Okay, which is greater, T naught or T? T naught is less than T. Because this is fraction, 1 by fraction is greater than 1, T naught multiplied by greater than 1, T is greater than T naught. So proper time is less than the time seen in the other frame. Proper time is less, coordinate time seen from another frame is greater. So this is called time dilation. That means time expands. This frame, an observer in this frame sees time expands. Here the time recorded by this frame is expanded to an observer in S. So this is time dilation. Okay, good. We have covered the two important facts of special relativity: length contraction and space and time dilation. Now come to the point. Minkowski space-time line element. Minkowski space-time line element. Minkowski space, what is Minkowski space? A space endowed with four coordinates: T, X, Y, Z. a space endowed with 4 coordinates is called Minkowski space. Now let two events in S are T, X, Y, Z and T plus dt, X plus dx, Y plus dy, Z plus dz. These are the two events. One event is T, X, Y, Z. Another event is T plus dt, X plus dx, Y plus dy, Z plus dz. Then the difference, the interval or difference, the difference is given by ds square is c square dt square minus dx square minus dy square minus dz square. This is called special relativistic line element or interval. Whenever you have two events, then the square of the separation between those two events is given by this formula if and only if the two events are separated infinitesimally. The two events are separated infinitesimally. In that case, the relativistic line element or interval is given by this formula. If you take a little greater, then you can write del t, del x, that is, you can write also this. But actual line element is not that. Actual line element is what I have written here. Okay. Next point and the last point of today's class is proper time. Unward line. In three-dimensional space, a particle is moving. Say, in three-dimensional space, a particle is moving. What you call the course of the particle? Path. Path of the particle. In special relativity, we call it word line. In special relativity, the path of a particle in special relativity is called word line. Okay, so word line will be given by word line T, X, Y, Z. But T cannot be measured independently of X, Y, Z. So actually you have no choice but to write X function of T, Y function of T, Z function of T. But now we have only 3 coordinates. You have to trace the path. If you want to trace the path, you have to have time in every point. So X at the time T, Y at the time T, Z at the time T gives you this line. But more 4-dimensional prescription is T function of lambda, X function of lambda, Y function of lambda, Z function of lambda, where lambda is a monotonic parameter along the. So whenever lambda changes, the point changes. Say I have this one line. Here lambda 1, here lambda 2, lambda 3. Every point has a different lambda, and lambda does not decrease, lambda increases along the path. Say the path will be moving in this way. So lambda will increase monotonically. What is monotonically? In the same fashion. It moves, it increases. Monotonic parameter. It increases. So as you give t function of lambda, x function of lambda, y function of lambda, z function of lambda, you trace out the one line. Okay. And what is lambda? Monotonic parameter. But is there any example that we can use lambda as this one or that one? Yes. For a massive body, proper time is the best choice for lambda. For a massive body, proper time is the best choice for lambda. Okay. Along the odd line of a particle, the infinitesimal difference between proper time from one point of a one line to another point of one line is given by c square beta square equals ds square. See, ds square is the one I have written little bit ago. ds square is the one I have written a little bit ago. And here this is theta is a infinitesimal proper time interval between two events along the one line. Along the one line between two events, the proper time interval is dt. Then c square is ds square. Now ds square can be written as c square, d square minus dx square minus dy square minus dz square. Now what? If you have this dx square plus dy square plus dz square, it is what? D square dt square, right? This is d square dt square. So here you get c square minus b square dt square d tau equals 1 minus b square by c square whole to the power half dt. You see? And this factor is gamma dt divided by gamma. We actually write sometimes right, sometimes we don't write gamma p. That means gamma is computed with the velocity v. This v. So this is the theta velocity by gamma p. Now, in a frame S, between 2 points A and B, between 2 points or lines, or 2 points in the line, between 2 points, what is the difference between proper time? That means we want to write, we have to compute tau integration A to B beta. That means along the one line you have 2 points A and B. What is the difference? What is the total proper time between these two events? A and B. A and B events have separation in proper time, which is tau. We have to integrate. So integration will give you A to B 1 minus B square function of t by c square whole to the power half. Here I have used the formula, just I have written a little bit ago. Now say this is in S. If the particle is at rest in S, then V of t equals 0, tau equals integration dt. Right? You follow this. That means if a particle is at rest in a frame S, then the proper time is nothing but the coordinate time recorded by a clock. If a particle is at rest in a frame, then proper time is nothing but the coordinate time recorded by a clock in the frame. Okay. Now if you define S prime and instantaneously rest frame for the particle. That means you are defining another frame S prime, and it is instantaneously rest frame. That means the particle is moving, but I have a frame, and I consider, I imagine that it is at rest momentarily, again momentarily. It is moving, but instantaneously it is at rest. At the time dt is equals 0, it is at rest. Then again it moves a little bit further, rest. Moves again a little bit further, rest. Infinite decimal rest frame. Then this formula should be utilized. Now, what is this? I have written little bit ago. We have found out what? Time dilation. What was that? T equals gamma T naught, or T naught divided by square root of 1 minus c square by c square. Now what is this? 1 minus c square by c square, divide this. So if you imagine this, if you take this factor, beneath this factor, then this is t, this is t naught, right? That means what? Proper time is the time recorded by a clock moving with the particle. Proper time is the time moving with the clock as the clock moves. So this proper time is invariant, because a particle's proper time, which is measured by a clock attached with this, cannot be defined by an observer S, Y, Z, X, Y, Z. It is an invariant quantity. The proper time is the time measured by the clock with the particle. No one can disagree with this time. So this is an invariant time. Proper time is an invariant time. So today this much. Thank you very much.